So today we're going to be looking into a specific type of function called an inverse function. And inverse functions are a little tricky at first, but basically they just reverse the effect of their original function. So to get started, let's look at some notation. Suppose you have a function f. The inverse of this function is denoted f inverse. And something I want to point out is that even though this looks like f to the negative 1, it's just called f inverse when you say it out loud. The inverse of a function, f inverse y, is equal to x if and only if f of x is equal to y. So let's look at an example to make this a little bit more concrete. So say you have a function h, which is the inverse function of another function, f, and let's say that f of 2 is equal to 7, and f of 3 is equal to 2. So we know by the definition of a function, when you input x into this function, it's going to result in this output y value. And we know that in an inverse function, when you put that output y, it's going to revert it back to x. It's going to give this x as now the output value. So for h, which is, again, the inverse function of f, when you put 7 into h, you're going to get 2. And when you put 2 into h, you're going to get 3. Let's take a look at another example. Say f inverse is the inverse function of f. In this case, f inverse of f of x is going to equal simply just x. And at first, this might be a little confusing, but if you really take a look at this, we know that this term here, f of x, this is just equal to y, right? So what this really evaluates to is the inverse of y, and we know that when we put y into the inverse function of another function, we're just going to get the original x value. So that makes sense. And it also works the other way around. F of f inverse of y is going to equal just simply y. And again, at first a little confusing, but if you really look at this inside term here, f inverse of y, when you put in the output y value into the inverse function, you're going to get the original input value x, right? So this just evaluates to x. So this is just f of x, which we know is y. There's another term I want to define that's kind of useful to know, invertible function. So if y is equal to f of x, and this is a function such that its inverse, x is equal to f inverse of y, is also a function, then we say f of x is an invertible function. So basically, a function is called an invertible function if if it has an inverse function. Okay, so this could be a little bit confusing. There's really two terms here. There's invertible function and inverse function. An inverse function is what we were just talking about. F inverse of y is equal to x. So in an inverse function, there's an original function, f of x equals y, and it's a function such that it undoes that transformation, where you could put y into the function and you can get the original x back. An invertible function is what we call that original function, y is equal to f of x, if it has an inverse function that exists. So not all functions, y equals f of x, have an invertible function. So the key question then becomes, how do we know if a function has an inverse function? And there's two requirements we check to do this. So the two requirements for an invertible function. The first is that the function has to be something we call one-to-one. And what that really means is that there's no two distinct x values which map to the same y value. And it might help to kind of look at this visually. We previously talked about how a function looks something like this. So if this is the domain of the function, maybe we'll say 2 and 3, and this is the range of the function, maybe we'll say just 1. Something like this is okay and is a function. So basically, every x value is mapped to some y value. But as we also saw, not every mapping like this is a function. So something like this would not be a function. So if the domain is 2 and 3, and the range is maybe, we'll say this time 1 and 7, and if 2 is mapped to two numbers, so in this case 2 is mapped to both 1 and to 7, that is a no-go. Each x value has to be mapped to exactly one y value. So that this would not be considered a function. What would an invertible function look like? So for an invertible function, it would look something like this. So if the domain is again 2 and 3, and this time we'll say the range is 1 and 7. This is what an invertible function would look like. So like I said, the first requirement is one-to-one. No two distinct x values which map to the same y value. So although this is a function here, this would not be considered a invertible function because we have two x values which map to just one y value. Here, each x value is mapped to just exactly one y value. So that means that this is a function where it is possible to reverse the transformation. And if you think about this on just kind of like a common sense level, it makes sense. Like say you had a function f inverse and you wanted to put 1 into that function. If you did that, how would you know if the original value was 2 or 3? It wouldn't be possible because that information has been lost. The second requirement is something called onto. And what this means is every y value is associated with at least one x value. And this one is a bit simpler. So if we had a domain that looks something like this, 2 and 3, and if we had a range that maybe looked like something like this, 1, 7, and 8, and the mapping was something like this would not meet the criteria for onto. So here, say again, we had that inverse function f inverse, and we put 8 into that. In this case, 8 doesn't map back to anything in the original domain, which would not meet this onto requirement. If we imagine we put, 8 into f inverse, what would that value be? There's nothing it's mapped to in the domain. So this is the f of x is not an invertible function. There's also a way to graphically check if a function is invertible using something called the horizontal line test. So this is a quick way to quickly check if a function meets the requirements of being an invertible function and how it works is if no horizontal line intersects with a graph of a function more than once, the function is invertible. And let's take a look at what this would kind of look like. So say we had a function that looks something like this. If we did the horizontal line test on this, for every y, we would draw a horizontal line and check that it only intersected once. So for example, here, it only intersects with the graph once here. And at every y, it's only going to ever intersect once, which is going to mean that this function is invertible. If we look at another graph, something like this, and we do the horizontal line test here, we can see that at several y's, it's going to have more than one intersection. Like there's 2 there, there's 2 here, 2 here, and this is going to fail the horizontal line test, which means that this function, the function that's graphed here is not an invertible function. So if you look at why this is, and we again think about the 2 requirements, remember the first requirement is the function has to be 1-to-1. So if we look at many of these y values, like this one here, this y value is mapped to 2 x values. And you can imagine, again, if we put this y value into f inverse, how are we going to know which x value that it mapped to? Or how are we going to know the original x value that led to this y value? We can't know that. So this is not going to be something that's an invertible function. Next, let's look at how to find the inverse of a function. So say we have the function 2x plus 3 is equal to y. How would we find the inverse of this function? So the first thing you have to do is to check to make sure the inverse exists. So first you check the two requirements. And an easy way to do this is the horizontal line test. Second, you're going to want to solve for x. So if we have 2x plus 3 is equal to y, we subtract the 3 first. So we have 2x is equal to y minus 3. Then we divide by 2. We have x is equal to y minus 3 divided by 2. And that is going to be the inverse function. So we would write that like this: f of negative 1 of y is equal to y minus 3 divided by 2. And finally, we go ahead and check that we correctly found the inverse. So the way we do that is there's two properties which we talked about. There's f of f inverse of y, which is equal to y, and we have f inverse of f of x, which is equal to x. So let's go ahead and plug in this inverse function. Let's go ahead and plug in this inverse function that we found into these two and see if we did properly calculate the inverse. So let's start with the first one here. So that is going to be this: f of f inverse of y is equal to y. So f is equal to 2 times x plus 3 is equal to y. So for x, we're going to plug in the inverse function. So it becomes 2 times y minus 3 divided by 2 plus 3 is equal to y. And that's going to evaluate to 2y divided by 2 minus 6 divided by 2 plus 3 is equal to y. And we know that that's just going to be y minus 3 plus 3 is equal to y, which is y is equal to y. That is correct. We got y here as expected. So let's go ahead and do this one now. Let's go ahead and move this up a bit. Okay, so in this case, we put the original function into the inverse function. So that's going to look something like this: 2x plus 3 minus 3 divided by 2. And if we solve for this, what we're going to get is this is just going to be 2x divided by 2, which is equal to just x, which is exactly what we'd expect.